We're going to start chapter 14 today, and chapter 14 is about chemical kinetics. It's like rates and things like that to affect your chemical reactions, okay? Chemical kinetics is the speed at which reactions takes place, and that's called reaction rate. And there's some things you can do to affect that, and we're going to talk about those, and you can actually calculate it. So we're going to look at some of this stuff as far as what happens when you have a chemical reaction and things you can do to change the rate at which it occurs. Okay, so the study of reaction rate is called chemical kinetics. Okay, you can actually, they have step-by-step view of the changes, and basically you're going from, you start with all reactants, you have no products, and then as the reaction occurs, you use up the reactants and you end up with products. And so they have a mechanism, and it goes step by step how you change from one to the other. Okay, so what can you do to affect reaction rate? Well, first of all, what is the state of the reactants? If they're a gas, it happens a lot faster. Okay, liquids, solids are the slowest, because again, think about the particles, how close they are. Before you can change them, you have to break those intermolecular forces. So, the physical state of reactants is one thing. The concentration of the reactants. Okay, as you increase the concentration to a point, you're going to make the reaction happen faster. The temperature. As temperature increases, usually your reaction happens faster. And then something called a catalyst. Okay, a catalyst is something that lowers the activation energy. It's called energy for a reaction to get started. And the catalyst itself isn't changed, but it helps change or control the rate at which a reaction occurs. Okay, so when we're talking about the physical state of the reactants, again, the more rapidly or readily they smash into each other, the faster they're going to react. So that's why gases are much better for that, because they're moving a lot faster. Okay, if they're homogeneous reaction, if they're all gases or all liquids, so if they're all in the same phase, if you take a gas and a liquid, it's not going to occur as if you take two gases or two liquids. So usually if it's a homogeneous reaction, if they're all in the same phase, it's going to happen faster. A heterogeneous reaction, and remember, homo means the same, hetero means different. Heterogeneous reaction involves, if you have solids, it's going to be much slower. Okay, the faster of these reactions occur, because if you want your solid reaction, if you have a solid and you want it to happen faster, it's better if it's in a fine powder, because you increase the surface area, you got more area for it to interact with, than if it's like a pellet or if it's in a chunk. And we know that when you're making a solution, if you have chunks in there and you're trying to stir it up, you kind of chop up those little chunks so that they're smaller, and then the reaction happens faster. Okay, so that is some of the things that can happen for your to increase your rate of reaction. Okay, another one is increasing reactant concentration. Okay, when you increase your concentration, you're going to increase your reaction rate up to a point. There's a point where it's saturated and you can't make it go any faster. But here they're showing steel wool heated in air, about 20% oxygen. Okay, here it is in 100% oxygen. So we're adding much more oxygen. It burns a lot cleaner. It burns a lot faster, because when here you're going to have to hold it in there, and when you're done, you're still going to have some steel wool and it's going to be like kind of charred. Here you're just going to burn it right up. Okay, and the reason for that is because you have more molecules, you have more collisions you have, the more you overcome those intermolecular forces, the faster the reaction occurs. Okay, temperature, if you increase the temperature, the reaction rate goes faster. There's a few that it's the reverse, but in most cases, if you increase the temperature, your reaction rate is going to increase. Okay, because the kinetic energy of the molecules is related to temperature. So if they're moving faster, they're going to bang into each other more, and then you're going to have more of a reaction occurring. Okay, so usually when you increase the temperature, you're going to increase the rate at which a reaction occurs. At higher temperatures, again, the molecules move much more quickly, and because they're moving around faster, they're going to bang into each other more. The energy of the molecules are going to have more collisions, and your reactions are going to happen faster. Okay, so when you're looking at reaction rate, if anything you can do to increase the collisions between the molecules or the atoms, depending on if it's an element, then you're going to increase the rate of reaction. Okay, so temperature, definitely, if you're increasing the temperature, increasing kinetic energy, they're moving faster. They're going to bang into each other more. Okay. And then there's the catalyst. I talked a little bit about this. A catalyst is something that you add, and sometimes it's responsible for making the reaction occur, but it doesn't affect the overall balanced equation. And by what I mean is, let's say you take hydrogen and oxygen gas. If you put them together, they don't make water. You have to do something for them to make water. You can add a piece of metal. A metal would be a catalyst. And on the surface of the metal, the oxygen gas and the hydrogen gas will bang into each other, and then they'll start forming water. So without that piece of metal, that's your catalyst. You don't have that reaction. When you're all done and you've produced your water, you can take that piece of metal out and it's the same. It hasn't changed. But without it, the reaction didn't happen. So it's a catalyst. Okay? They affect the kinds of collisions. So they change the mechanism. That's what a catalyst does. In your car, you have catalytic converters. Okay, catalytic converters were added to cars, and what it does is it increases the rate of oxygen to some of the exhaust particles. So instead of getting carbon monoxide, CO, you get carbon dioxide, which, breathing carbon monoxide, you don't breathe for very long. Breathing carbon dioxide, you're fine. So, we have these catalytic converters in our car, and they have metals. Unfortunately, it's usually platinum. So if you ever have an issue with your catalytic converter, get it fixed right away, because if you lose that piece of platinum, it's really, really expensive. Platinum's worth more than gold. But anyway, platinum in that case is the catalyst that allows extra oxygen to be added to your exhaust products so that they're safe, they reduce pollution. Okay. Catalysts, we have many catalysts in our body. We call them enzymes. So an enzyme is a biological catalyst. Okay, their job is to make reactions happen or increase their rate or decrease their rate depending on the reaction itself. Okay, so that's what a catalyst is. It's something that affects the rate of reaction without being changed itself. Okay, so when we're looking at reaction rate, really what rate is change of concentration over time. You can look here, remember a triangle is changing, and this is concentration when you use these brackets. So the concentration of some substance over the change in time. Okay, and again, I put all these in there. Anytime you see a triangle in science, it's changing. So change in concentration would be the first one. And when I talk about concentration, it's molarity. Okay, and then again, same thing here, change in time. So types of rates that are measured, they have what they call the average rate. So you do over a whole reaction. You'd have instantaneous at one certain point, what's going on there. And then initial, where you started. Okay. Usually average rate is about the only thing, you calculate. And that's what I'm going to have you guys do a few of. But you can do all of these. Initial is really simple. You just look at it. Where did it start? Okay. So here's a reaction. We've got an organic compound. We're going to add water. And when we're done, we get a different organic compound and HCl, which is hydrochloric acid. So you can see here we have the times and we have the concentrations, and they give you the rates. Okay, the rate of reaction is measured using a concentration change for that reactant over time. So we started, here's our time and here's our concentration is 0.1. And your concentration is going to go down for your reactant. If I have my product here, that would increase because I'm using up this and I'm making that. So here they have the average rates. You take this divided by time. Okay, and so as you go down, what you would do if you wanted to find these rates, what you would do is you take the difference between these two and the difference between those two. Because remember, you can see the rate is the concentration of my reactant over time. You can't see that, I'm in the way, I'm sorry, but it's change in concentration of C4H9Cl. You can't see that. And then it's over change in time. Sorry, I don't know where to put myself so that I don't get in the way of my slides. But anyway, so if I wanted to find it at this point, I would just take the difference in these and then over time. Okay, if I wanted to do it at 200, I would take this, this minus this. And then if I was doing it at 200, well, my time would be 200 because 200 minus 0. Okay, so anytime you're trying to figure out the average rate, you're going to take, the concentration at which point, subtract the difference between them, and you're going to get a negative number because this is going to decrease, and then the difference in time. Okay, here's an example. We start out with moles of A, and we haven't made any B. We're saying A is our reactant and B is our product. Okay, so we start a reaction and we're getting less A and we're getting more B. Here we still got a little bit more A than B. They're really close. And then as the reaction goes on, now you can see we have even less A and more B. And eventually we'll have all B and no more A. Okay, so we're given the concentrations. We got 20 seconds and 40 seconds. And we need to calculate the average rate of the reaction over the time. Okay, so and then the second one, they want you to do the average rate for the change in concentration. All right, so remember we said that change in temperature or change in concentration, in this case it would have been A, over time. So if I go back here, okay, here's where it started at 1, and if we're doing, we're doing for the 20 seconds, okay? So I take 0.54, that's my concentration at this time, minus 1, okay? And then my time, well, it goes from 0 to 20, so it'd just be 20 seconds. So that would be, and again, it would be a negative number because I'm reducing its amount. So that would be my rate of disappearance. And again, that's why you can say it's a negative number, because you're disappearing, you're getting less and less each time. And again, it's just subtracting the concentration you're at, where you started, and then the time. Okay, that's how I would do the first one. Now my next question is, the average rate is given by change of concentration. Okay, and so what am I looking for? Oh, the minus sign. Okay, so I have another question here. Calculate the appearance of B at 40 seconds. Okay, so we're going to figure out B here. Okay, we ended at 0.7 moles. Okay, so 0.7 is where we ended, and we started the first time. We're going to do it for 20 seconds because if you look here, I'm sorry, I have to keep going back. At 20 seconds, we had 0.46. Okay, I can't start it here because there isn't any. Okay, so I'm going to go start it there. And so I take my 0.7 where I'm at 40, and then I subtract where I was at 20. And again, my time is going to be 20 because this was at 40 seconds, this was at 20 seconds. So now I'm doing appearance, so it's going to be a positive number. And that's the rate at which, so for, I increase, the rate I'm increasing is 0.012 molar per second. That's how much I'm increasing. And again, I took at whatever, in this case 40 seconds, whatever my concentration of my product was, minus, in this case I did it for 20 seconds, and then I do that. If I wanted to do it for the whole thing, I could do 0.7 minus 0, and then here I would have 40 seconds. I'd go 40 minus 0. You could do it that way too. Okay, if you're doing what they call instantaneous rate at what happens at a certain point, you have to draw like what they call a curve, the slope of the line, and you get a little curve here. And then what you do is, the thing about rates, they don't just go straight across down. They tend to slope as the rate occurs. It tends to like mellow out a little bit. Okay, so if I want to do instantaneous rate at a certain point, I have to use the slope because it changes. It's not straight down. So what you do, sometimes chemists need to know what rate it's occurring at right now. You just take, like in this case, I would take this minus this, these two concentrations, and then I would do this time minus this time. Okay, so you have to do your slope that way. It can be a little weird sometimes to get your slope in there because like sometimes you want to go all the way to here, but it has to be straight down. So basically you take your slope like here and you just go straight down. And again, that takes away that little curve that's happening there. And then again, it's just same thing. It's concentration, difference in concentration. So it would be here to here, and then here to here as far as your time. Okay. So initial is really easy. It's just where did you start? The initial would be 0.1. That's where you started. But if you want to figure instantaneous, you have to kind of straighten out your curve of your line because the slope has to be straight across. And then again, it would be from here to here, and then the time from here to here. Okay, and it shows you that. Okay, where am I at? Oh, I'm done. Sorry, we'll pick this up next time.